Hi everyone, this is our last video for chapter 4 and it is on linearizations and linear approximations. So this is another application of derivatives, and before we dive into exactly what this is, I'm going to show you where we actually use linearizations. So if we've got this function f of x equals x squared, we can really easily find f of 2 by just substituting 2 into it. So 2 squared, we would get 4. That's easy, you guys know how to do it. F of 2.1 is a little bit harder, not because substituting 2.1 in there is hard, but because if you don't have your calculator, you're going to have to take a second to write it out and whatever. I mean, hopefully we can figure out that 2.1 squared is 4.41. But either way, it's still a little bit harder to evaluate, right? So what we're going to do is we're going to start using tangent lines instead to do some approximations. So since a tangent line stays very close to the graph of the function when it is near the value at which it is tangent, we can use tangent lines to estimate function values. This process is called creating a linearization, or really just using a linear approximation. So we're using the tangent line to estimate or approximate the actual function value instead of substituting in. So I'm going to show you guys what I mean by this. Let's look at the graph of f of x equals x squared. Alright, you guys know how to graph that by now for sure. We've got a nice parabola that looks like this. Alright, and then we want to look at the tangent line at x equals 2. So at x equals 2, we're right here, and we want the tangent line to this function. So the tangent line would be through like that. Okay, well now if we look at f of 2, we already know what that is. F of 2 is 4. Well, if we try to find 2.1, here's 2, so 2.1 would be roughly right here. We can see that that's really close to the actual function value of at 2.1. Alright, so that's why we're allowed to use this, because they're very close to each other. So let's look at algebraically what this means. So f of x is x squared. We're still using the same function here. We want to write the equation of the tangent line at f of x equals, or I'm sorry, 2f of x at x equals 2. So the equation of the tangent line, we know that we need a point and we need the slope. They told us that the point is tangent at x equals 2, and we can get the y value of that by just substituting it in. So 2 squared is 4. That means the point that we are writing the equation with is 2, 4. The slope, we know, means that we need the derivative. So f prime of x is equal to 2x, and that means that we can just do f prime of 2 and get 4. So now we have our slope is 4, and our point is 2, 4. So now we can actually write the tangent line. So y minus 4 equals 4 times x minus 2. This also asks us to actually approximate the value of f of 2.1. So what that means is we are going to take 2.1 and substitute it in for x. So y minus 4 equals 4 times 2.1 minus 2. That means we can start to simplify here. Y minus 4 equals 4 times 0.1. And we know that 0.1 times 4 is really just 0.4. And then we can add the y over, or the 4 over, not the y. So we get y equals 4.4. What that means is that 4.4 is approximately equal to f of 2.1. I said that backwards, but you know what I mean. F of 2.1 is approximately 4.4. All right, well, when we evaluated it up here, we said that 2.1 squared is 4.41, and we got 4.4. Those are really close to each other. I mean, it's pretty, and it's some pretty basic algebra that we did here. All right, but that's how close these linear approximations, wow, I can't speak, can actually get us. It's kind of cool. All right, so let's look at some more examples here. So now we have this table that we're looking at. F is a function that is differentiable for all real numbers. Table gives us f and f prime values between negative 1.5 and positive 1.5. The second derivative is greater than 0 for negative 1.5 to 1.5. So this is also asking us to write the equation of the tangent line at x equals 1. And then we're going to use this to approximate the value of f of 1.2. So this first part here is actually asking us to write the equation of the tangent line. So again, we need our point and we need our slope in order to write the equation of the tangent line. So the point, we know that the x value is 1. And if we look at our table here, x equals 1, then f of x is negative 4. And the slope means f prime of 1. So again, we go to 1 for x, and we want f prime this time. That means that our slope is 5. So we can write the equation of the tangent line as y plus 4 equals 5 times x minus 1. Now, this is the equation of the tangent line. But sometimes they'll actually ask you to write the linearization of x. All right, so I'm going to put like a part B here, and we're going to call this the linearization of x. All right, that's the words that we actually say, and that is L of x. So when they ask you for the linearization, or the equation for the linearization, then we're going to write L of x. So really all we have to do is move the 4 over to the other side and change the y to an ln of x. So you guys know that when we start using function notation, that really stands for the y. All right, so L of x then, the linearization of x, is 5 times x minus 1 minus 4. This is really the standard form for linearization. Okay. So now we're going to do L of 1.2 so that we can get an approximation. So 5, 1.2 minus 1 minus 4. That means we get 5 times 0.2 minus 4. So we get 1 minus 4, which tells us that the linear approximation at x equals 1.2 is negative 3. So what that right there means is that f of 1.2 is approximately negative 3. All right, we are going to do the second example in class. We're going to do it together before you guys start on your practice. So go ahead and go to the next page for me. and we're going to start talking about the accuracy of these approximations. So I already said that everything we do in here is just a rough estimate, okay? None of these are exact answers. So we need to talk about determining whether our approximations are over or under estimates. So we can determine whether our linear approximation, will be an over or under estimate by looking at the second derivative. So we've looked a little bit at taking the second derivative, but we haven't actually done anything with it. So now we're actually going to do that. But this curvature is called concavity, and it can be determined by examining the second derivative. So f double prime of x. Okay? So when we talk about concavity, we can talk about concave up or we can talk about concave down. So concave up usually looks like this. We usually tell you to think about a cup or think about a smile, all right? But concave up rhymes with cup, so it's kind of easy to remember that. But when we look at something like this, if our function looks like that, and I draw a tangent line, I can draw one here, I can draw one here, or I could even draw one here. There are lots of places I can draw tangent lines on that. But when we look, all of those green tangent lines are underneath our curve, which means that anytime a function is concave up, it's going to be an underestimate. Okay. When we talk about a function being concave down looks like a frown. Get it? Haha, I'm so funny. Anyway, concave down, if we start drawing tangent lines to that function, we can draw one here, or one here, or one over here. All of those ones are going to give us overestimates. So in order to determine if the linearization is an over or underestimate, we need to look at the concavity. So if we look down here, this example 1 is exactly the same as the one we just did on the page before. So we looked at the equation of the tangent line at x equals 1, and we used that linearization to find that it is approximately -3. Now what we're going to do is determine, is that an over or an under estimate? And you'll notice that it does ask us to justify our answer. That's going to be an important part here. This is huge on the AP exam, all right? Well, in the directions here, we were told that f double prime of x is greater than 0. So what that means is that our function is concave up. By the way, we should back up for a second. My bad. Concave up means that the second derivative is greater than 0. That might be some useful information. Yep, it definitely would, Miss J. Concave up means that f double prime of x, the second derivative, is greater than 0. Concave down, then, means that the second derivative, f double prime of x, is less than 0. That might help a little bit, wouldn't it? Yes, it definitely would. So back to this example. F double prime is greater than 0 on this interval, which means it is concave up. So what we are going to look at then is concave up. I'm going to draw a sketch of it. Concave up looks like that. So if I start drawing my tangent lines, oops, that looks more like a secant line, sorry. My tangent lines, those are all underestimates. All right, so I don't want you to memorize which one is which. Actually draw yourself a picture and think through it. But we know then that we said f of 1.2 is approximately -3, and this is an underestimate. Because f double prime of x is greater than 0. And that's all it is. All right, so we will do the second example down here when we do the other example in class. And I will see you guys tomorrow for some practice.